for this test.
Not great.
What, on Monday, next Monday?
It'll be 2 weeks from tonight.
Next Tuesday?
This is the final for lab.
Oh, that's fine.
Well, we can take it either Wednesday or Thursday.
2 weeks from
Yeah, I am making it available to on Wednesday if you want to do it on Wednesday. If you want to take them both and skip Thursday, I wouldn't have a problem with that. Since I'm already going to be here and do it. I
Yeah,
don't
we have to
care.
come in Friday.
Yeah, they're not gonna repeat it last time.
So we're missing, what, about 8 people?
Why do you stop talking?
Attendance is down.
Getting close to the weekend or something?
Everything's from last night.
Okay, so I have, I'm gonna cover 10:30, looks like it's only 4 pages, and 10:90, it's about 8 pages. So, it's on switches. I got the picture of breaker for some reason. Okay, there's an typical aircraft circuit breaker. Some of you may have seen these before, but this is, the black part is the only part you'll see. That's 2 amps.
Scott, do you wanna?
Oh, yeah. That'll help.
This is on which page? 1034?
You don't have this picture, but I threw this in. It's pertinent for some reason. And this is a fuse, but it's a resettable fuse, so it's a circuit breaker. It does the same thing as these little glass fuses I've been fighting with these past few weeks. But that one blows at 2 amps, and then it's resettable just by pushing it back in. We got all kinds of stuff in here.
More closer to classes.
We started with switches. Looks like I've got several presentations in here. So there's a typical switch. We'll get into that. You've heard double throw, double pole, that type of thing. If not, I'll explain it to you. So there's the actuator, the actual switch lever. They're showing a bushing in the case. There are movable contacts. Always got to do that. Don't hamper it again. I think I have a picture. Yeah, I have a picture. Okay, so we have output terminals, the little sliders. You may have seen these in other applications where you've got that little sliding sleeve that slides over the top. This one has 6. I'll show you the next picture. It's a little more explainable in color. This switch here, these are almost like a teeter-totter. The gold are your contacts that are the yellow part. So this switch will make contact with either these 2 positions or these 2 positions. And then it's identical on the other side, but they're completely separate from each other. So basically you have one switch inside one housing and they operate together. But we call it a switch, but it's as though there are 2 switches inside one. An example where you might do that was I could put power to this little part right here and have a green light and a red light. So I could switch it, and this little teeter-totter right now in this position is making these 2 contacts. I could have a red light, switch it the other way, and then the power would go to the green light, the red light would go off. And if I wanted something relating to that, I could tie in on the other side. The light might be 12 volts, but I might run something. I'm trying to think if I could be running a fan or a sign or something related to my red or green light. Well, for one, I could run a hydraulic pump. And I might want a red light that's warning that the condition or what's going on with the pump. It could be the red light stating that the pump is running and to stay clear of a certain area. And then when I switch it the other way, it turns the pump off, and I get a green light that it's okay to enter an area. And they could be different voltages. One could be AC and one could be DC, because they are two separate paths inside one housing.
Variable voltage kind of like?
I could have 12 volts DC and I could have 110 volts AC over here if I wanted, because they don't intermix. But they're in one housing because they're associated with each other. When I flip this switch, I want two things to happen at the same time. And that's what that switch looks like. This part has a spring inside it, and this switch you pull, and if you notice, it's got this is the bottom of the handle, the actuator, and then it's got a point here, and then there's a ridge right here. And when you pull it, this will pull out and clear this, and then you can switch to the other position.
That's a safety feature?
So you don't bump, this switch is not bumped into a different position. You have to pull it, actuate it, and release it. It'll spring back and lock on either side of this ridge. I can tell just by the number of prongs. This is a simple on-off switch. That's got a cover, guarding cover.
Well, what's the third slot down there?
The third slot is the housing. So this housing, the manufacturer can create whatever switch they want. They just make the same housing. This is a little late in the game, but this explains open and closed circuits. But we're talking about switches. So we can say we make a contact or we close a contact. And in that situation, we are closing the circuit and the bulb will light. We can break a contact or open a contact and the light goes out. Okay, poles. There's poles and there's throws. A switch pole refers to the number of separate circuits that the switch controls. A single pole switch controls just one circuit. A double pole switch controls two separate circuits. So the first switch we saw was a double pole switch. A double pole switch is like two separate single pole switches that are mechanically operated by the same lever, knob, or button. The number of throws indicates how many different output connections each switch pole can connect its output input to. The two most common types are single throw, double throw. So if you think of throw, when I was talking about I could actually connect electricity back here, I could connect the power here, and I can direct the power to here or here. That would be a double throw. So if you literally think of it as throwing, I can throw that electricity that direction or I can throw it that way. So the throw is the number of paths I can send that connection.
So a single in my house is like a light switch.
A light switch. So this one here would be a single throw, single pole.
Because you can only throw it
I can only throw it one direction.
one direction.
And it's a single pole because it only has one path. Whereas this one has a pole across here where these interact with each other, and then the three on the other side interact with each other.
So you could have like multiple throws but one path, or
Oh, it can get crazy. I mean, we can get switches that have a knob on them, and you have layers of contacts, and when you rotate it, you make and break different contacts all the way through.
so is that two poles?
This would be a double pole, double throw.
Okay.
Double pole is I have two separate switches,
Right.
two entirely different circuits. A pole would be a circuit.
Okay,
So this has two entirely separate circuits, it's a double pole. I can send that power, I can throw it to that connection or that connection. So I can throw it, either one will throw that power in two different directions. So here's where it gets crazy. Single pole, single throw, and that was that other switch that had the little red guard on it, would be the top one. The common is what we're bringing into the switch. It could be a ground or it could be a positive, but the common is the one that stays. So I can move, if I were to connect this to a ground, when I switch it here, this would be ground, or this would be ground, one or the other. But this would be the common connection to either of the places I can throw it. So that's a single pole double throw. Single pole meaning it's a single circuit. But I can throw that common to the 3 or I can throw it to the 1. Double pole, single throw. So here's a switch, it's on off, but they're two separate circuits. Double pole, double throw was the first one I showed you. So that 2 and the 5 would be that middle little connection. And then the 3 and the 1 and the 6 and the 4 would be the other two that I can redirect to. But they are mechanically tied together. So when I switch this, when I move it this way, the 3 goes to 1 and the 6 goes to 4. 3-pole double throw. So 3 poles means there are 3 individual circuits, and I can send them double throw. I can send each one of those circuits in 2 different directions. And then 4-pole double throw. So it's 4 pole being 4 separate circuits, and I can throw them in each of those in 2 different directions. And it can continue to build from there. There's the NO and the NC is normally open or normally closed. So in the top left, the enable is my making the contact. This would be a button, whatever I use. It could be your refrigerator. There's a little switch inside that turns the light on and off. That enable would be that little button that's sticking out. That's how you're manipulating the contacts. So the single pole, single throw, normally open would be like your doorbell on your house. So yeah, when you push on it, you make a connection, but it is normally open. When you let go, it remains open. Normally closed would be the opposite. So I might put this on the door frame of my car for the dome light. So when I close the door, it pushes it to the open position. I open the car door, the switch relaxes because the door is open, and it closes and makes a contact, and the light overhead comes on. So that would be an example of a single pole, single throw. Would be that switching a door frame. It is normally closed. The door is your car door is normally closed, which will hold it open. But the switch is designed to be normally closed. So when you physically open the car door, the switch relaxes to its normally closed position, and you get a light. Single pole, double throw. So I have single pole, meaning it's one circuit. Might be 12 volts, might be 110 AC, but I can throw it to 2 different directions. This has a select, so I can actually select one or the other, and it will stay there. The enable would be a momentary single pole, single throw. So I have 2 separate circuits, and then as soon as I let go, it's going to open again.
so you have 2 knobs, or
Well, this one is showing that they have 2 buttons in one assembly. See, the enable are separate, and the select has 1 lead that goes through both contacts.
But
So
it's
that's
on
going to have 2 buttons.
So it's on the same circuit. That's what it's saying.
It's it's almost like that first switch we saw. And I can't say that because the separate dash lines tell me they operate separately. So you're gonna have two different buttons.
But
I
it'd
can't
be on
think-
the same circuit, right?
No, that's
Oh, a single pole.
yeah, you're right. Single pole, single throw.
Just two buttons, that's all, so.
I want to say
So
that
the-
may be a typo, and you may have just first time we noticed that.
But it's a single pole, single throw.
Well, couldn't that be like two different light switches in the same room?
Well, it's the blue tells me that it's in one assembly, but I think that's a double pole. I think that's an error because this is a single pole. Here's a single pole, single throw. See here?
Yeah.
And the blue tells me it's one assembly. So I've got two parallel circuits.
Double throws.
So I'm quite sure that's a double pole single throw. Single throw meaning when I enable it, that common can only take one path. Yes.
And isn't it marked by the enable? Like it's enable.
Enable tells me that it's a momentary, where a select is going to stay there.
So you're thinking
Oh, so this
now,
is a quick press button.
I'm quite certain that this is a double pole single throw.
so there'd just be one knob.
No, when the enables are separate like that,
There's two knobs.
it tells me there's two switches, knobs, whatever.
Okay.
But it
This
was
when they do this and it goes through both of the
Then there's
contacts,
just one.
then there's
I'm
one.
sorry, I'm confused about something. Select is like just a knob, right? Where it
Not
stays.
necessarily.
No.
This is just the contacts inside, and we can make contacts several different ways. And I think that's my next picture. I'll show you. So double pull, double throw. See, this is the same, pretty much the same as that one, except the two surfaces work together. I got it. There it is.
The two times.
2 times 2. So it is single pole, single throw times 2. So you have two buttons, and my clue was here: double pull, double throw. They're
They're just
times-
encased in the
it's
same
times 2.
housing.
Because it isn't each. There's two buttons, two ways to actuate the switch, and each one of those is a single pole, single throw. That's why it says times 2. So,
So would that be on something that is an emergency button or something?
I can't think of where you'd have two switches at one time at the enable in one assembly.
And they would be two separate
It'd be
circuits?
two different ways of contact.
Would that
Two
be
different
like
ways. of-
Normally I would see them like this,
Mhm.
like.
Oh, how about a master arm switch?
Well, what I'm thinking for this one, see, but that's enable. That's a momentary. This is a select.
can that be like I don't know, maybe I'm being far fetched, like an ejection seat if the push button is
Well, you know what I'm thinking is, if I were to put this in the door frame of a cargo door,
Okay.
I could put that one in a cargo door, aircraft or luggage compartment. So when you open the door, one of those switches turns a light on inside, and the other contact sends a light to the cockpit saying you got a door unlocked. But normally I would expect to see that where they always operate together. I don't have a better example for the single pole, single throw times 2. So double pole, double throw, and it's got to select. It's one switch. This is the first switch we saw. The very beginning. And then here's a double pole, double throw times 2. So that it's one switch assembly, and they work separately. I mean that single pole, single throw, trim, maybe your trim switch on the.
It's on momentary.
I don't know, maybe but I think there's two switches and they have an up and a down.
Yeah.
So that wouldn't maybe not exactly. We'll come to the type of switches to answer John and the question about how we actually the different ways we can actuate. Okay, alternate with no latch down. So this would be close to your doorbell. There's buttons that we push in the cockpit that are only momentary, and the once we let go, it pops back up. So these stay up. The only time they stay down is while your finger's on them. So it's normally open in this situation. You push down, it's closed. This one is a latch down, so the button will physically raise up, but the switch will stay closed. You push it again, it opens, you release it, it remains open. So it's an on-off, not too unlike a pen. You know, you get to one selection, then another, then back to the first, then back to the second. But the plunger, the button itself will rise up. Alternate with latch down. This is almost the same, except the button will rest down, so you can visually see that it's been actuated. You push it again, it'll pop up, and it's off. And then a momentary. This would be close to your doorbell. It only makes contact when you're pushing down on it. Once you let go, like a push to test, doorbell. Normally open, normally closed. So you can do either. That would be more like a doorbell. Normally open. You want an open circuit because you don't want your doorbell on all the time. Normally closed. This would be your refrigerator door. You close the refrigerator, it pushes on the switch, and your light goes out. There's an example of how a momentary switch works. This would be obviously it's going to be flush mounted across here. Here's your push button, and this spring here is what pushes the button back to its original position. This plunger is attached to the button, and when you push it, this part moves. I should have a pointer. These are your pins on the bottom of the switch. This is where you slide the little wire connectors onto. So these posts are mounted at the bottom of the switch. This here, and this particular style switch is like a washer, and it's on the end of this this post. So when you release the button, this actually moves away from these two contacts. I think I have both pictures. Yeah. So that one's normally open. So you can see the pins at the bottom don't have a contact. This spring here pushes this washer or this surface against those. The shaft does not. So when I push this, the whole assembly moves, but once this makes contact, like here, if I continue to push hard on this, the spring is pushing the contacts together, but the shaft will actually slide on, continue on through. They do that so you don't, if you're pushing on it really hard or jamming on it, you're not going to break anything in here. So you can push on it, but it's the spring that's pushing the contacts together. Oh my. 2-position toggle, 3-position toggle. So this would be a 2-position. It's just on and off. The none, it says on, none, off. The none means there's not an option. There's no option to stop in the middle. It's either going to be full up or full down. So you can have an on-off, on-on, or on-on. What's it? On is momentary. So a 2-position toggle doesn't necessarily tell you how many contacts there are. You can have one that's a switch that's on-off. One switch, just like on the wall. There's an on and on. So the on-on is something is on when it's down and something else is on when it's up. Might be like a jump light. If I've been in craft where guys would jump out the back, you've all seen the movies where the light's red, then it goes green. That would be an example of an on. They would always be in the red position, and then when I switch it to the other position, the red light's going to go out and the green light gets power, and then everybody jumps. And then an on, none, on is where the switch is normally in an on position, but as you move it to the other position, you are doing something momentarily, and when you release it, it'll spring back. Almost like the key, I'm trying to think, almost like the key on your car, but it's fuel boost. I'm trying to think where you might use an on. Generally, the on is something else, the momentary on. You're switching something on momentarily, but you don't want it to remain on after you let go or walk away.
You could put it on as a primer on there, right?
You could be a primer. So it's something's on and then something else is on until you let go of it. But it won't allow you to leave the second thing on. Once you walk away and let go of the switch, it springs back to the original position. So then with a 3 position, we've got a center. And the center is always off. So I can have an on and on where my red light's on and then my green light is on, but in the middle it's off. So if we're not jumping, if we're just hauling cargo, I don't need the red light on I don't need my red jump light on. I can put it in the middle position and it's off. On, off, momentary. So I could have something on, or I could switch it off, or I could move it to the other position and hold it and cause something to happen. And as soon as I let go, generally it'll spring back to the off position. And so on, I could have on and momentary on. So it's in the middle, and would be more like a trim switch, where you may have a trim motor, something that moves. You push it in one direction, a motor drives. You know what that one is? That's the windshield. That's the window switch on your car. You push it one direction, the window goes up. You let go, it stops. You push it the other way, the window goes down. You let go, it stops. And then an on would be you've got three different things you're turning on. 3 options. An example might be lighting. You might have low lights, medium, and bright. But the on tells you whatever you're adjusting or changing something will always be on.
What is that? There's a distinction between throw and position.
There's a distinction between throw and position. Among 2 position switches, there's a single throw, on, none, off, and double throw, on, none, on. I'd have to think about that. With the distinction between throw and position, the throw is when it's in a position where it's sending power in one direction. Like these in the off, this is a double throw switch. The switch is off, but I can throw power this direction or that direction. But in the middle is a middle position, but that middle position isn't considered a throw. Since I have three possible detents where the switch can sit, it's still only a double throw. This would be a triple throw down here.
Okay.
But this would be a double throw.
Isn't it describing a difference between position and throw switch? On the bottom?
Um,
2 position, 3 position.
On, none, off, on, none, on. Okay, well this one would be, to me, a single, I don't know, I can't say for sure what they're trying to explain there. If you have more clarity than I do. But again, in these off positions, that's a position, but it's not a throw. So if I were looking at the switch, it has a 3 position, doesn't mean it's a 3 throw. It could be only a double throw. Because I can only throw power in 1 of 2 directions.
Okay, I think I see that. On.
And one at the bottom though, on. That's 3 different positions.
So this one would be a triple throw.
Everything
A single pole triple throw. Because I have on position, I have 3 different things I could do.
3 different things.
Yeah.
And then at one time, what was it?
Something's always going to be on, but my common might be 12 volts into the switch, but I can send the 12 volts here, or here, or here.
Something will always be on there. That's a big switch.
Okay, this asks John's question about how you can manipulate the switch. There's all the different ways. So those little dashed lines that we saw earlier, where we were manipulating or moving the contacts, these are the different ways that represented by that dashed line. We got toggles on the front, rockers, paddles, push buttons. These are not all typically aviation switches. There is a another type of switch. That'd be a rotary switch. There's what that rotary switch may look like on the inside. And I was telling John, these switches can get crazy because this layer here, you can have several different options where when you rotate this, you've got a contact in there that's going to rotate and connect this one from the one opposite or the one next to it. I mean, they can put just about any configuration in here. And they can stack these things. I don't know if I've had a picture of them stacked. I don't think so. But these switches can be long and do many things with just rotating. So that's an overhead panel. I don't know the aircraft.
Those are all the circuit breakers.
Those are not all of them, but those are all circuit breakers.
Smoky bag. Smoky bag.
What do you mean not all of them, but they are?
Okay, these are all circuit breakers, but they're not all the circuit breakers. Because this is overhead, and generally behind on large aircraft, almost the entire wall behind the pilots is just rows and rows, floor to ceiling of breakers. I have a picture. That's kind of interesting to look at. You can tell a little bit about the airplane. I can tell it's got a left bleed and a right bleed, so it's a 2-engine. There's fuel boost, left, right, start, left, right. Yep, it's got prop heat in here somewhere. Air conditioning down there. There's that switch. Okay, we talked about relays before, and this also talks about bus bars. A bus bar in electrical power in distributing refers to a thick strip of copper or aluminum and conducts electricity within a switchboard, distributing board, or other electrical apparatus. So I could actually have a strip that has power, an open strip, and I can tie into it. Usually older aircraft, you'll see this. More modern aircraft, it's more modular in a box, computer-looking type
What do you mean
box.
modular? Like,
Modular mean, I guess it's going to be in a rack. You're not going to have exposed strips like this. This would be in a covered area. There would be a panel or a cover over it, but when you expose it, you can lay and bolt in other wires to get power. This power off, the tap off of the power. And this is what they've done here. This is a battery bus. So this is connected to the battery, and these are circuit breakers, like the ones we saw. That symbol represents the pole type of breaker. So I'm showing a master switch to the cockpit and a battery contactor. This would be a relay. This assembly all the way from those blue contacts down to here.
It comes back in circle. I'm sorry, it comes back in recycle.
It doesn't. What it does is this right there is my battery, and then I have my battery bus. So that switch right here, master switch in the cockpit. A lot of airplanes, when you first walk in, they're completely dark. You go in the cockpit and you hit the battery switch, and you'll get some illumination in the cockpit and a little bit of other things going on until you get other source of power going on, either an APU or an external power. But you may just need to check a couple of things, turn the battery on. But that one switch is what's turning the battery on. This is what's happening. Is the switch, no matter where it is in the cockpit, you don't want to run. Battery cables are thick. You've seen them when you've disconnected a battery in your car. You don't want to run that all the way up to the cockpit. You don't have to. It adds weight. It's not efficient. You may not even need. This battery bus may only be a foot to 18 inches from the battery itself. So what you do is you've got a switch, there's a ground close by, and then there's a coil. This is what a relay, this is a relay. So this magnetic coil is gonna pull this contactor down and close this connection. And now you're gonna get 12 volts, if that's 12 volts indeed, to your battery bus. So you go in the cockpit and you flip a switch, the things come on. These wires here can be very small. So it's a remote switch. I go up in the cockpit, I hit this switch, I complete a ground through a coil to the actual battery, and the magnetic field pulls this closed, and now I've got power to my battery bus. But it's just not practical. Relays are used quite a lot in automobiles and aircraft, because you don't want to run, you can't run these big fat cables that are as big as my finger all up behind the panels. So you run small wires, plus this, like I said, the battery and the battery bus may only be this far apart. So you don't want to run this big fat cable all the way up to the cockpit so you can turn it on and off and back to the bus bar. You just run it straight there, but you put a relay in the middle. But you turn it on and off remotely from the cockpit. Okay, that's that. That's switches. Switch you. I'm not sure what this is. Okay, I think we covered it. Switches explained. Okay, I think what I covered. This is just extra stuff I've thrown in. Nothing about that. Okay, 1090 is batteries. How you doing? You guys you surviving this? I know this part hurts.
Just painful.
I know, it's painful for me too. I think this is 8 pages, so I'll make it quick. A primary cell is a battery that's designed to be used once and discharged. So a primary battery is a throwaway battery, like what you put in a flashlight. Dry cell is the most common type of primary cell, and it's basically designed with a metal electrode or graphite rod acting as a cathode or positive terminal, immersed in electrolytic paste. When in a discharge condition, an electrochemical reaction takes place, resulting in one of the metals being consumed. This is why you can't charge a battery that's not a rechargeable battery, because the process of electricity coming from that battery is because another metal is being consumed. And when you apply power back into it, that metal just doesn't reappear or grow back. Because of this consumption, the charging process is not reversible. Attempting to reverse the chemical reaction in a primary cell by way of recharging is usually dangerous and can lead to a battery explosion. These batteries are commonly used to power items such as flashlights. So that's a primary cell. A secondary cell is rechargeable, like a lead-acid battery. It is a kind of electrolyte cell in which the electrochemical reaction that releases energy is reversible. The lead-acid car battery is a secondary cell battery. The electrolyte is sulfuric acid. The positive electrode is lead peroxide, and the negative electrode is lead. You won't be tested on that. A typical lead-acid battery consists of 6 lead-acid cells in a case, each producing 2 volts. So the whole battery to produce 12 volts is going to have 6 cells. The other commonly used secondary cell chemistry types are a NiCad, nickel cadmium, nickel metal hydride, lithium ion polymer. Those are all secondary cells, and the charge can be reversed. Lead-acid batteries in aircraft are similar to automobile batteries. It's made up of a series of identical cells containing sets of positive and negative plates. The positive plates are lead dioxide, negative are spongy lead, and the electrolyte is typically sulfuric acid and water. So there is a typical aircraft battery. It's got a knob and an attachment that makes it easy to connect and disconnect, and also prevents you from hooking it up backwards. This is a drain line. If you pop the cover off, it's going to have little screw caps on top, not too unlike a regular lead acid battery, so it can be serviced. It's covered and covered tightly, and then this hose goes overboard. So if your battery does boil over or boil up or whatever, just makes a mess, it doesn't run down inside the aircraft. It is contained under this cover around those little caps, and it will vent through this and down a little plastic pipe out to the ground or wherever.
They don't have a little reserve where, when it boils over into a reserve.
I think they do have cups, now that you mention it. Most of them will have a cup.
Yeah.
You're right, have a cup, but I think that cup also will have as a backup, so that cup doesn't, if the cup does overflow. You're right, thank you.
No, these type of batteries you can go back and get a reservice, you said?
Yeah, so if this, and like an automotive battery, if it's completely crapped out, then there's a core charge, and then whoever receives it will take it apart and rebuild it and sell it again, just like we do with automobile batteries now. So that's it. So you can see the 6 individual cells. That's a 12-volt battery. Each one of these cells produces 2 volts.
And all it is just two chemicals interacting with each other.
It's
What it's
2
being-
different types of metal in a what they call it, a electrolyte.
Okay.
So battery voltage is determined by the number of cells connected in series. A 12-volt battery has 6 lead acid cells. A 24 volt has 12 cells. The most common battery rating is the amp hour rating. This is a unit of measurement for battery capacity. It's determined by multiplying the current flow in amperes by the time in hours that a battery is being discharged. So if I have a 100 amp hour battery and I put a 1 amp fan or light on it, it should last 100 hours. If I have a 100 amp hour battery and I put a half amp load on it, it should last 200 hours. And I say should because it's not perfect. It's not going to run 100 hours, then it's done. It does start to taper off. But at a minimum, it's supposed to produce the number of amp hours that it's labeled as. Battery with I think that's telling you what I just told you. A battery with a capacity of 1 amp hour should be able to continuously supply current of 1 amp to a load for exactly an hour, 2 amps for a half an hour, or a third amp for 3 hours before becoming completely discharged. Heavy discharge current heats the battery and decreases its efficiency and total amp hour output. So if you're running a higher load, if this is I'm not sure if I can read that, how many amp hours that is. But if it's 100 amp hour and you're running 90 amps, it's going to go faster than you would expect. The time it heats up and it's less efficient. Where is it? 24 volt. That thing weighs 55 pounds. That's a 222 amp hour.
So that would last for 22 hours then.
At 1 amp.
1 amp. Is that typical for battery, 22 hours? I guess-
No, they vary quite a bit.
Yeah.
You know when you've seen truck batteries and car batteries. It's little tiny efficient cars have a smaller battery because they don't need the amperage, where a truck needs more amps, and so it's going to be a bigger battery and it's going to have a higher amp hour.
like
They say cold cranking amps also tells you how much it can crank and how much you can get out of it, like if you're starting or doing, getting a high draw on it.
How do you get that? Cranking?
Cold cranking amps, it's stamped, on automobiles, they stamp it on there, it's on the label.
How do you get it? CCA.
How do you get it? So if you had a large engine, a big truck, and it was hard to start, you really want a battery that's capable of high cranking in.
So when there's no math to get it, how do you get it?
No. There may be, but it's going to depend on the materials, the density of the materials, the size of the batteries. It's determined by lots of things.
But do they compensate for like this, the size of the cells and stuff, or how much chemicals, like concentration?
The larger cells are going to larger plates. These are a chemical reaction between two dissimilar metals.
Right.
So you have electrons moving through the electrolyte from one metal towards the other. So if you have a larger surface area, you're going to get more current. So a larger cell, a fatter, larger material is going to
I
have.
need more current, right?
If you've ever seen the battery on an electric forklift, I mean it's about as big as this table, not including this, and they're huge. And that's because it takes a high draw, and they want to get a lot out of it over a longer period of time. So it's just big. Okay, life cycle determined by the number of complete charge and discharge cycles a battery can perform before its normal charge capacity falls below 80% of its initial rated capacity. Battery life can be anywhere from 500 to 1300 cycles. Various factors can cause deterioration of the battery and shorten its service life. The first is over discharging, which causes excess sulfation, the white powdery material if you've ever looked down in, if you've ever serviced a battery. Second, too rapid charging or discharging, which can result in overheating the plates and shedding of active material.
What would cause,
Over discharge.
why does overheating
When you
cause the shedding of active material?
when you've got anything that's hotter has more atomic motion. With all the particles are moving. You've got chemicals and metals where the electrons are more active, and so it's more susceptible to shedding or breaking down. I don't know how a better way to describe it. Go ahead.
So the heating is caused by
There's lots
the
of things.
movement of electrons?
Yes, and you can also have a hot environment. If you've got a vehicle that's in heat, like your truck is idling in the desert and it's 120 degrees out, that battery under that hood is going to be hot too.
Yeah.
And you may be charging it with your charging system. So heat can come in different ways.
But if you have a low battery and you hook it up to a charger, you have a 5 amp, 15 amp, 25 amp, and you just crank it up to the highest amount.
You can, yeah, if you
What
need
is causing that to get warm?
you're forcing electrons in faster. That's the best way. You're creating friction. Normally, if you really need that battery, you're not going to kill it. But if you're doing that all the time, you're going to shorten its life. If you need that battery, I'd bump it up and bring it up quick. But normally they make chargers now that do this. But you've got all the switches, and if you do a little read up, it'll recommend that you start low
Right.
and start bumping it up as your percentage of charge returns.
So it's actual movement?
It's almost like filling a container. But I'm trying to think of the friction aspect.
Or the electrons just being forced absorbed too quickly?
There is an absorption.
This is a chemical reaction.
It's a chemical reaction, and I want to say absorption. The electrons are moving in a different direction. They can only move into the material so fast. Absorption would be the best term I could say. It's not like filling a container where there's no resistance. You're going to find resistance. I
Right.
mean, if you've noticed with your cell phone, it gets warm when you're charging it.
Mhm.
I don't know if you've noticed that or not.
Yeah, anything really.
It's friction, and you're meeting some resistance. The electrons flowed out, and now you're forcing them back in the opposite direction.
Mhm.
You're gonna get a battery class in here, is my understanding. I've seen, there's a class that's just on batteries. Lead acid battery test methods.
How long is that gonna take?
How many frames do I have? I know we're gonna do a break here, so.
No, just saying.
Oh my goodness, just like.
We're just having a whole class on batteries.
Yeah, I was just thinking about the whole battery class. I was like, I'm gonna have to pay for it.
I don't know if it's a whole battery class, but I know where there's a class that encompasses batteries. We got a whole battery station out there. Anyone ever use a
Yeah,
hydrometer?
yeah.
This is a testing one? State of the charge.
So the state of charge depends upon the condition of the active materials, primarily the plates. However, the state of charge of a battery is indicated by the density of the electrolyte and is checked by a hydrometer. The instrument measures the specific gravity or weight, as it's compared with water, of the liquids in the battery. Batteries used today are made up of plates, lead oxide, and a solution of electrolyte. This solution consists of about 65% water and 35% sulfuric acid. The specific gravity or weight of the solution increases as the battery charges and decreases as the battery discharges. As the battery discharges, sulfur moves away from the solution and towards the plates. The opposite is true as the battery is charged. The sulfur returns to the electrolyte solution, so it'll be heavier or more dense. So you can get a condition of the battery charge by, well, it's a suction. You squeeze it, put it in the liquid, draw some into acid into the tube, and the little floats have values on them. When a battery is tested using a hydrometer, the temperature of the electrolyte must be taken into consideration. So on the inside, the markings will have temperature ranges. The specific gravities on the hydrometer will vary from the actual specific gravity as temperature changes. No correction is necessary when the temperature is between 70 and 90 Fahrenheit, since this variation is not great enough to consider. When temperatures are greater than 90 Fahrenheit or less than 70 Fahrenheit, it's necessary to apply a correction. So you'll typically see 3 bands, 3 ranges on that float on the inside. Oh, and I wrote in here PPE. Who knows what PPE is?
Personal
There you
protective.
Whenever you work with batteries, you gotta be careful. I was pulling a 24-volt battery out of a C-130 one time, and it started to slip, and I had to go to the ground with it fast, and it hit the ground hard. I didn't do a full drop, but when I did that, the electrolyte came shooting out of one of the tops, and the guy standing next to me got it in the eyes.
Ooh.
Now, we got him rinsed pretty quick,
Wow.
and we sent him to the clinic. He was fine, but you just, you know, I talk about accidents occasionally. You never know. I mean, we've all spilled things. That's how quick accidents happen. And once an accident starts, it's hard to avoid it. It's gonna.
The odds of it shooting straight up in, right in the eye.
He was standing next to me, and I think he moved forward as I started to lose control of him, which put him in closer. So NiCads. This is on the test. The electrolyte is potassium hydroxide, or you can remember KOH. So the materials in the nickel NiCad are nickel hydrate in the charged positive plate and a sponge cadmium in the anode. And the electrolyte is potassium hydroxide, KOH.
So any of that before test material? I didn't hear you say this on before stuff. Everything before is on
Usually if I cover it, I usually tell you when something's not on the test.
test.
But I'm mentioning this because it's a kind of an acronym. When I cover stuff, you can pretty much almost guarantee that it's covered unless I tell you it's not. But I'm usually teaching you concepts. But if I'm talking about a name or a an acronym, letters, I try to give you a heads up.
Why do we? It doesn't make sense why we would have to know specifically that.
I don't
That's
know,
usually jobs.
but that's a great question.
Okay.
Moving on.
Don't miss it on the
Okay, we'll go to break here in a minute. Give me a couple more pages. Okay, I'm gonna try. I apologize for all the reading. The advantages of a NiCad battery. It's a lower selling price, no special conditions to be shipped. It can be easily stored and doesn't damage under most normal circumstances. Also, it's a simple and fast to charge. It'll take a higher number of charges. Sounds great. Sounds like the perfect battery. And it can last much longer. Finally, low temperatures do not usually affect the NiCad, and it accepts a charge on the first try. Some batteries, when we were talking about charging them in stages, some batteries won't take a charge the first time. The lead acids.
Can they be stored for?
Lead acids will lose, and I think pretty much every battery will lose charge over time. But this one, it does state that it does last much longer. So compared to conventional batteries, the NiCad will hold its charge longer. So it's a lot of great advantage. I mean, it's lower selling price, faster and simpler to charge, lasts longer, temperatures usually don't affect it. But then the disadvantage is it has a relatively low energy density, so you're not going to get as many amp hours out of it.
So this is great for cars.
And well, we use them in airplanes too.
Yeah.
I mean, it doesn't mean it has a relatively low energy density, so you may have to go to a little bit larger size
So this
battery.
would probably be what they use in the golf cart when they have like 12 of them or 6 of them, whatever it is, right?
No,
So is
generally
that
not.
Is it no?
Those are generally lead acid batteries, and they're 6 volts most of the time.
What about cars these days?
I don't know that I think we're away from, I haven't seen NiCads in a car yet.
Wow.
Usually I'm seeing these NiCads electronics, but I want to think there's been some larger NiCads.
Because
Any of the smaller, I don't know, main battery for an aircraft is a NiCad? Have you seen or heard?
But I mean all electric car.
so
Yeah, I don't remember. I haven't been following electric car technology. I know that's changing all the time. This relatively low energy density tells me that it may not be the ideal for electric car.
Yeah.
Because you're not for the weight and size, you're not going to get as much energy out of it. And it says, but it can often self-discharge. So maybe when it says last longer, the life of the battery is longer.
Is there a way, if it's discharges, to bring it back? Isn't there a react? If you're taking an old battery that's been stored, isn't there a way of doing that? Getting this, I forgot.
It's the type of battery generally.
Yeah.
This one says no special condition. Where is it? Simple and fast charge. So the NiCad is not going to be one of those batteries. It's simple with no special. But Scott was saying he's your charger. You have a charger with several ranges?
Yeah.
Yeah, so you'll go with a certain amperage initially to start the process.
Yeah.
And then you'll gradually come up as it gets higher. There's usually a chart. Now they make smart chargers that do all that for you. They can measure what's going on in the battery and it adjusts on its own. I want a new charger. They make them now that, that sulfation, that white powder that we see inside the cells when you look down in the liquid. They have chargers that will actually reverse that. It does a pulse charge. It just boom, boom, boom with charging. They can actually cause that to re-dissolve. It's a much more expensive charger, but batteries will last far longer.
That's what I was talking about.
They call it a pulse charger.
Yeah.
Okay, I think this is the last little bit we got. An inverter is used in some aircraft to convert portions of DC power to AC. This AC is used mainly for instruments, radio, radar lighting, and other accessories. The These inverters are usually built to supply current at a frequency of 400 cycles per second, hertz, or 400 hertz. But some are designed to provide more than one voltage, for example, 26 volt AC in one winding and 115 volts in other. So you can have those windings, you can have windings within windings and separate. So when you have this would be for a mechanical inverter. We have static inverters now, and probably a lot of you have them. You plug it into your cigarette lighter of your car, and you can plug your 120 volts into that. That's just called a static inverter. We say static because it has no moving parts. Older aircraft, and when I started with the reserves, we had 130s and they had mechanical inverters like these. They were under the cockpit floor and they were noisy. We had a pair of them. So the radios in the airplane didn't work off of DC. So if we needed to tow or call the tower, we'd have to spin these up. And the floor would vibrate. If you were in there for any length of time with these running, you had to put headphones in. They were very annoying. But now, modern aircraft use static inverters. And that's it. So yeah, that's just DC. You're using the aircraft battery DC to spin this generator and it creates AC power. You guys ready for a break?
Yep. They were talking about when I was listening to the radio about how they use now the brake systems to recharge the batteries. Have you
Yeah,
heard
on
of that?
cars.
Yeah. You-
Yeah, regenerative brakes.
So that's a
how does
press
that-
switch, kinda like that.
how does that work?
Well, when you step on the brake, I mean, everything's done for you. I mean, it takes, but see, you do that in an electric car. You could, I guess you could probably do it there'd be no advantage to have it on a conventional gas car because you got plenty of power to keep your battery charged. But when you have an electric car,
Yeah,
you're
talking
driving
about
motors, and when you step on the brake, they actually do the opposite. You now they become, instead of motors, they become generators, and you take that power as you're decelerating, going down a long hill. You can send that power that the wheels are driving back into your battery. There's my reminder for you guys to break. So come back around